Hey, so this is the second page of chapter 4's like graph of molecules. The second page of it, the front side, and then we'll do the back side, or at least part of the back side. So we had talked about this a little bit last time. This molecule right here, this is like the one that has the correct electron count, except that it's got a lone pair. There we go. This is the one that has the correct electron count. If you want to count it, you got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we are good to go on our electron count. So that's all good on that guy. And then we want to look at those last 3 columns because that's what's not filled in for a lot of the structures on here. And the fact that these are blue, this is significant. So if we want to look right over here in the columns, we have formal charges, resonance, and polar. All right, so right here, our structure has resonance, and we know that because our double bond could be written in the position we have it in, or it could be written there, or it could be written there. I have to show all 3 of them. When I see resonance, I have to show them all. So I'm going to zoom in, and I'm going to put one over here that has the double bond, that has the double bond going in that direction right there, and a single bond, and a single bond. My single bonds are the ones that just get the electrons, lots of the electrons. And then this one only fits 2. Still need the brackets because it has a charge. And then I'm going to do the other structure, which has a nitrogen, and it has the double bond going down, and then an oxygen and an oxygen. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. And if you count all these, you're going to get that they all come out to be that same value. You also have to write them with arrows going back and forth between them. Now remember, the real structure is somewhere in between. And if you're wondering about bond length, so people will say, how do I figure out the bond length? Well, there's a total of 4 bonds in that and 3 positions for it. So, 1, 2, 3, 4 bonds divided by 3 positions. That's going to give you a bond length of about 1.3 for all of them. What's the shape? Well, we have 3 regions like we say here, so it's definitely trigonoplanar. Don't have any lone pairs. And the molecule thinks of this double bond region as just one region. It doesn't think of it as 2. It thinks of it as one region. So there's a region, there's a region, there's a region. So even though I know there's more electrons crammed into that space, the molecule just still says, well, that's just one space that's being occupied, even though there are more electrons. Low lone pairs means that our electron geometry is the same as our molecular geometry. So those are the same. And you just have to remember these angles. They're 120. You just got to remember them. Now, we've said it has resonance. We want to know, well, does it have polarity? Okay. So remember, for polarity, if you've got lone pairs, you're definitely polar. If you have no lone pairs in the same atoms on the outside, then you're going to be nonpolar. That's because the look of this thing over here, I've got them kind of drawn a little funny, but trigonoplanar means that it looks like this. They're perfectly evenly, like imagine 3 ropes coming off of someone perfectly evenly. And I know that that one's a double bond. The molecule doesn't sense it to be enough different to cause polarity on the molecule, is the best way to put it. So this one, it is not polar. And then, well, does it have formal charge? And we're probably going to see it does have some formal charge. We're going to look at the nitrogen. So nitrogen right here. I'm going to make it kind of small. Remember, you do formal charge for each element. So nitrogen has a value of 5 valence electrons, and then we're subtracting out 4 bonds. So that gives us a value of +1. So in all these structures, the nitrogen actually does have a +1. We do it with just a plus on him. Now we're going to look at the oxygens. 6 minus 4 dots minus, I'm going to do the double bonded oxygen. So I'm doing like that one right there. So the double bond is 6 minus 4 dots minus 2 bonds, and that gives me 0. So I don't write 0 as the formal charge. Now I'm going to do the single bonded oxygen, and that gives me 6 minus 6 dots minus 1 bond, which is -1. Again, I would put that with a 0 and negative, so both of my oxygens right here are -1. So anytime that I've got those lone pair oxygens, those are -1s. So can we fix the structure? Well, the only problem in trying to fix these structures is that we are going to need to make more bonds. And the question is, can nitrogen have more bonds? Well, look at him. If you look on the periodic chart, he's in the second row. So nitrogen is a second row element. Can second row elements do more bonds or more electrons around them than 8? Because he currently has 1, 2, 3, 4, 5, 6, 7. He has 8. No, they can't do any more than 8. So even though we have some formal charge issues, I can't fix this by putting some of these oxygen electrons on that bond. I'll show you where you can fix it is when you do have something that's a higher value. And I can't change that nitrogen. So there's no way that I can make like more double bonds to nitrogen without losing some of the atoms. You can try it. You can try making a double bond or a triple bond, but you won't be able to fit all the atoms around the nitrogen and keep nitrogen at 8. So the rule of thumb is, well, that's just the way it is. That molecule is just off. And the bond lengths do come out to be 1.3 when we check it. So let's see what we can find out in some other cases. So then we have our CO2 molecule. So for our CO2, COO, when we do this one, if you do it all with single bonds, you end up with 18 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. You end up with 20 electrons. So this molecule right here has to have some double bonds, double bond, double bond. So that gives us 16 right there. Is this resonating? No, because you have to have a single and a double bond for resonance. So this is not resonance. So no resonance. Is it polar? Well, the bonds are polar. I got that one backwards. But what happens? They canceling each other out. So this one is overall not polar. And then what about the formal charges? Let's see how they turn out. So let's take the carbon. So he has 4 minus 0 dots and minus 4 lines. So that gives me 0. So he's in a really good place. And then the oxygens, both of them are the same. So 6. That's how many their valence is. Minus 4 dots, minus 2 lines, gives me 0. So those are all 0. So that's a great structure, a very comfortable, happy structure. Now if we look at O3, so O, this one's going to need a double bond. If you count it all up beforehand, you won't get the right structure. So this gives me 2, 4, 6, 8, 10, 12, 14, 16, 18. This gives me my 18, which is good. Notice this is 3 regions. 1, 2, 3. That's why it's named trigonal planar. And when you have a lone pair of trigonal planar, it's called bent. And you do need to know these. You're going to have to memorize these ones. Bond angle on something like that. And this should say 120. Less than 120. And that's a correction on that one. All right, so then the question is, do we have resonance? And we already have this marked with a check mark of resonance, and we know this has resonance because we have a double bond and a single bond. So I can do it again. I can paste them down here, but I'm going to change where my double bond is. So now my double bond is on this side. I need a pair of electrons here, and I'm going to take off one of the pairs over here. Notice I don't need brackets because the species is neutral, but I do need my back and forth arrows. And again, my bond length is going to be a 1.5. So definitely have resonance. Then do we have polarity? Well, we have the same external atoms, but notice for sure we have this lone pair. And unless it's linear or square planar, that lone pair is pushing these guys off. So you can see like we're off kilter going those directions. They aren't evenly canceling each other out. So we are polar. The bonds are polar, and overall the molecule is polar. Let's check our formal charges. So let's look at the central oxygen. So that one's going to be 6 minus 2 dots minus 3 bonds, which gives us 1. And then let's talk about our double bonded oxygen. 6 minus 4 minus 2, so that's 0. And then our single bonded oxygen. So that one is going to be, that's the oxygen, not 0. Oxygen is 6 minus 6 lone pairs minus 1 bond is -1. So this right here, the central one, is positive. And then this guy right here is the -1. Can we fix it? Well, we have all the same atoms, so like we can't do anything with the atoms. And then the question is, well, if you tried to make this like in a double bond right here, then this guy is going to have too many electrons. You can play around with it and try to make it work. But I'm telling you, it's not going to work no matter what you try to do, because you've got this issue again that the oxygen in the center, it can only fit 8 electrons. So even though we have formal charges, we can't fix those formal charges. And then we're going to zoom in on this guy right here. His structure, it's going to be C-O-O-O, double bond. He's got a charge, 2 minus, let's see if he adds up to 24. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So he does add up to 24. Notice we have this situation. We have oxygens, all the same elements on the outside, and we've got a double and a single bond. So definitely we have resonance for this guy too. So we want to draw the other structures. I'm just moving that bond around and making sure the right compounds get the right bond, the right electrons. And then we're going to draw them, line the arrows between them. The other thing about resonance is resonance also gives stability. In organic chemistry, you'll see that resonance is one of the reasons why, like acid strength varies, base strength varies. Resonance affects how long species will exist. In a reaction, has a whole lot of different effects. So resonance does matter. As far as the regions, we name this trigonal planar because it's 1, 2, 3 regions, even though one of them has some extra electrons in them. Notice they're all spread out. So we have the same atoms. We have no lone pairs. They're all spread out. So if you were going to look for polarity in that molecule, what we're seeing is that we've got something kind of like this, this, and this. It's like 3 people standing around someone with tug-of-war ropes that person, I don't know, would tied to their waist or something, equally spaced. Then they're going to, basically the person in the middle won't be moving, and the electrons don't end up overall causing a structural polarity. So there is no polarity. And then again, central, we've got the carbon. So this is 4 minus 0 minus 4 bonds. So that one's 0. He's good. We're going to talk about the double bonded oxygen. So that one is 6 minus 2 minus 4. Those are the, I said that I wrote those down in reverse. 6 minus 4 dots minus 2 bonds. So that's 0. And then the single bonded oxygens, those are going to be 6 minus 6 lone pairs minus 1 bond is minus 1. Notice that central atom 0. We start making more bonds or taking bonds away from that central atom. Again, we're going to have issues because he can only have 8. We're going to get past that rule in just a minute. Notice, though, that this is a polyatomic ion. It has resonance. This is a polyatomic ion. It has resonance. You should expect resonance for those guys. So we're going to, this was the one where I told people to go back and to fill things in. I'm going to go ahead and fill out what those structures should look like, though, to make sure that you're getting the right ones. So this left one. So S goes in the middle. And we have an oxygen, and an oxygen. And we had a double bond there. So we've got 6, and we've got, let's count them, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we're good on our counts. Notice, though, we have a situation with the same elements on the outside. So I don't need brackets because it's not charged, but I do need to show a double bond going that way, and that way. And that way, and that was the single bond. Don't forget the ones on him. And then you need the arrow to go between them. We're going to check mark that. Yes, this has resonance. I think it was the final, second from the end column. So yes, this has resonance. This is the resonance. This is the polar. And this is the formal charge. Got to fix that next time. So other questions about this molecule. Is it polar? Same atoms on the outside. No lone pairs, so it's like a person with 3 ropes coming off of them, equal tugging, nothing's going to happen. So it is not polar. And what about formal charges? So this is something where you're going to see things happening. All right, so sulfur has 6 minus 4 bonds. So right now sulfur is +2, which is not a great situation. Oxygen is 6, and I'm doing the double bonded oxygen. The double bonded oxygen is 6 minus 4 electrons minus 2 bonds. That one's 0, so that one's good. Then we have single bonded oxygens, and we are 6 minus 1, which is -1. Okay, before I go over there and I start putting things in with the pluses and minuses, this is a case where formal charge will fix the molecule because sulfur can have more than 8. So what we're going to do, here's how you fix something with formal charge. If it can have more than 8, we're going to take a pair of electrons. I'm going to take this pair right here, and instead of having them there, I'm going to move them so that they're being donated to the bond. I am not increasing or changing any of my electron counts. I haven't changed my electron counts. I've just added an extra one to the bond. So now I have 2 oxygens that are double bonded, and in this situation only 1 that's a single bond with that situation. And if you look at my sulfur count is now 6 minus 5 minus 0. You may be seeing this. Where do we need to go to get this guy all the way formal charge correct? Can we do more? We can. We're going to come over here. We're going to erase this, and we're going to do that. So now, check this out. Our sulfur is now 6 minus 6 bonds, and I don't have any lone pairs around him. I'll say -0 minus 6. That gives us 0. So this structure is a structure, and notice I don't have any single bonds at all yet. Now I only have my double bonds, and I have 3 of them. So that guy is so much of a better formal charge structure. When you go and you look at it, guess what? All those double bonds are the bond length we find in the molecule. We don't find any resonance. Ha ha. I know, great, right? You're like, I just started understanding resonance. Now you're telling me there's a crazy case? Yeah. So you might just want to remember SO3, or just maybe check your formal charges at the very end. When you have an atom in the middle that can have more than 8, and then you've got oxygens on the outside, that's a kind of a tricky scenario. So SO4, PO4, those ones will be doing it. So now I'm going to erase all my resonances. I'm going to come over here, and I'm going to erase that one because I don't have resonance. Notice that I am still trigonal planar. I haven't changed that. And I don't have any lone pairs, so I'm still trigonal planar here. So that's that molecule. This is craziness, right? So now we've got SO3 2 minus. So this has an extra pair of electrons on the sulfur. So S, O, 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 1, 2, 3, 4. Now I believe this is the one. 2, 4, here we'll count it. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And notice it says 26. So I can put that lone pair on the middle like that. Notice that I need brackets and a 2 minus charge. Now I have 26. Yay for 26. Now you're probably thinking, why don't we do the formal charge count before we write down all those resonance structures? Okay, so let's do it. So sulfur has 6 minus 2 lone pairs minus 4 bonds. Oh, look, that one came out to be 0 this time. Let's do our double bonded oxygen. So that's 6 minus 4 electrons minus 2 is 0. And then we do have the 2 single bonded oxygens, and they are 6 minus 6 minus 1 equals -1. So if we were to do something to the sulfur to try to fix our oxygens, we could make like one of the oxygens go down to 1 by putting more bonds on the sulfur, but it makes the sulfur change and also start having a formal charge. So you don't want to move things around if moving them generates a higher formal charge. So like if I were to put this down here to make that bond, that sulfur's formal charge is going to be 6 minus 2 minus 5 bonds, which is -1. So fixing the oxygen on the outside unfixes the sulfur, so you don't want to do that one. So we're going to stop right there. We're going to say, okay, we can't do anything to fix that middle atom without messing up everything. So that would mean that this is the correct structure. So that means I do need to draw 2 more structures. So I'll draw one double bond up and one with the double bond to the right. Don't want to lose that lone pair on the sulfur. So this shape, the main shape is it's something that has 4 regions. 1, 2, 3, 4 regions. So that's main shape is tetrahedral. Notice it has a lone pair, so it makes it be trigonal pyramidal. And the bond angles on the tetrahedral are 109.5, but when there's a lone pair, it makes it just a smidge less. Is this polar? Well, it's got that lone pair. So what that means is there's some space that's being occupied. So instead of it being like an equal pool, like we've talked about before, where you're looking down, now what's going on is like we're like kind of pulling downwards. It's like these guys have ropes that are going down and there's like an empty space. So again, a lone pair with the same central atoms, unless it's linear or trigonal, square planar, is going to result in something that is polar. And then we have SO4 minus 2, so SO. And 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I'm pretty sure we're going to need at least one bond. So let's count these guys. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. All right, we got him. Now, remember, you're thinking, okay, is this really something that's going to have resonance or not? All right, so let's see. How's our formal charge count on this guy? All right, so we've got sulfur, which is 6, minus, right now we have 5 bonds. We have 0 lone pairs and 5 bonds, which is 1. And then we have 3, oh yeah, I usually do the double bonds first. So we have our double bonded oxygen, which is 6, minus 2 minus 4, which is 0. And then we have our single bonded oxygens, which is 6 minus 1. It's okay if you're seeing a pattern. So now I have an issue with my central atom being positive, and then all of these ones being negative. So I can fix that central atom in the same way that I fixed the central atom up here. So I can do it by making another double bond. So I'm going to take like this lone pair right here, and I'm going to like make it become the double bond. I'm not erasing electrons to do this. I'm just moving them in that direction. So now sulfur, I do new count here. Sulfur is 6 minus, well, sorry, he doesn't have any lone pairs. and 6 bonds, which is 0, so that's great. And now I have 2 double bonds and 2 single bonds. That's better than the situation I was at before. If I try to move him into here, I'm just going to generate a formal charge back to the sulfur. So even though I'll get rid of the oxygens, I'll generate one on the sulfur. So you don't want to do that. You don't want to like trade one formal charge for another. So we do have a situation where we could write those double bonds in different ways though. So we could have, I could keep this one here and I could make it go up here. And I could do one where I kept this here and I made it go across. I could do one where let's see, I moved him there. Trying to think if I can do a third one. I can do it like this. I can do one, I think I've got one more match for him. Silver. See if I got them all. Bottom to the left, bottom up, bottom right is that one. And then the right, left, opposite, and down's already done. And then on the left position, bottom, up, left, opposite. And then, oh, I haven't done the ones for the top position. So oxygen to the sulfur, right like that. Sorry. Here, this I haven't done that one. All right, so you can see all these. All of these would need brackets. They would all need to be filled in. You guys loving this? So this is just like a harder exercise to see. But they all need brackets. They all need arrows all going all between them. He's quite a bit of a character right there. In all cases, we have 4 bonds, which is tetrahedral. We have no lone pairs, so we are still called tetrahedral. And our bond angle is 109.5. Polarity, well, remember, polarity doesn't worry about if it's a double or a single bond. So I don't have any overall polarity because I don't have the lone pairs. And I do have all those resonance structures. We did NO in class, but I just wanted to point out this was one where everyone was wondering, how do you know how to draw this? Do you draw it like this? Or do you draw it? I got a few possibilities. Do you draw it like this? Or do you draw it like this? 2, 4, 6, 8. 10, 11, or do you do it like this? So this is where those formal charge rules come into play, especially well. And so we're going to jump over and look at the formal charge. We won't have resonance because we only have 2 molecules there, so there's not going to be any resonance. And also you can go ahead and say that the structure is linear because it's just between 2 atoms, should have the 180 degrees. The question is, which structure is the right structure? So we're going to test the formal charge of the first one that's drawn right here. So on this one, we have oxygen is 6, minus 4 dots, minus 2 bonds. So he's 0, that's good. And then nitrogen is 5, minus 3 dots, minus 2 bonds. So that's 0. This is a good structure, right? Like that. Let's try one of the other ones and see why they don't look as good. So we'll try this one right here. So this oxygen is 6, minus 5 dots, minus 2 bonds. 6. Sorry, I'm thinking too far ahead here. Can't write and talk. So 6 minus 3 dots minus 2 bonds gives us 1. And this is 5 minus 4 dots minus 2 bonds gives us minus 1. So notice now we have a structure where both of them have a charge. So this one right here is still way better. And then if you like doing my little counting thing, because I kind of like it, it's faster. So this is 6, 5, 4, 3, 2. So this would be a plus 2 on him. And it's not like a real point. I'm just trying to emphasize. And then N is 5, 4, 3, 2, 1, 0. So that's 0. So he wouldn't have a charge. But again, we have a +2 on that one. This one was a -1. And this was a +1. And then over here, we have nitrogen. Again, that's not anything real, just where I'm putting my pencil. So 5, 4, 3, 2, 1. So that's a +1. And then oxygen is 6, 5, 4, 3, 2, 1. That's a +1. So all of those, notice they don't follow good formal charge rules. This is where formal charge is very, very useful, is knowing the correct structure is like that, with more electron density on the oxygen, which is as it should be. That's the final formal charge rule. So is it polar? Yes, it's a linear molecule with 2 different atoms. And they do, if you need to check, they do have a electronegativity difference of 0.5. So they are polar. We also should check this guy, this xenon guy that I had skipped past. So if we're doing the formal charge for him, xenon is 8 minus, and then right now he's got 1, 2, 3, 4. Wait, I think I left a lone pair off of xenon when I was drawing this one. Let's just double check off lone pairs. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42. So we got our 42 now. So our xenon has 8 minus 2 minus 5. So he is right now +1. Our oxygen is 6 minus 6 minus 1, which is -1. All of our chlorines are the same, and they are 7 minus 6 minus 1 is 0. So the chlorines are fine. Can we fix the oxygen and the xenon? First question, can xenon have more than 2 electrons? I'm sorry, more than 8. Yes, it can. So let's go in here. We're always taking the lone pair from the oxygen guy. Let's make this like that. I didn't change my count. You can double check the count. It's still 42. But now what I've done is I've made it so that my xenon is 8 minus 2 lone pairs minus 6 bonds, which makes my xenon 0. And then my oxygen is 6 minus 4 lone pairs minus 0, which makes my oxygen 0. So all these are good in this molecule. And we do find that is a double bond length in real structures, not a single bond length. So do we have resonance? Well, no, we don't have resonance because we don't have other oxygens in there. It's not like you can only do resonance between bonds of the same atom. There's not other oxygens to do resonance with, so we do not have any resonance. And then are we polar? Well, we have different atoms on them to begin with, and on top of that, we also have the lone pair. So yeah, we are definitely polar. What's he called? Well, I've got 1, 2, 3, 4, 5, 6 regions, so the electron geometry is octahedral. But he's got that lone pair, so it's square pyramidal. It still has the 180 and the 90-degree angles. And if we just want to finish out these top ones here, this one, he's all good to go. There's nothing funny about this one. And so the carbon is trigonal planar. No lone pairs, still called trigonal planar. Bond angles on that are 120. Is it polar? Yes, it has different atoms on it. Does it have resonance? No, there's no other place that double bond could go. Formal charge. So carbon is 4 minus 0 minus 4, which is 0. That's great. The oxygen is 6 minus 4 minus 2, which is 0. That's great. And the hydrogens are 1 minus 0 minus 1, which is 0, which is great. You will find that the smaller structures are the only time that, most of the time, like on the other pages, if you check formal charge, they'll probably all come out being 0. All right, so then we've got this top one. So we've got 4 regions. That's tetrahedral. That's for the electron geometry. For the molecular geometry, that lone pair matters. It turns it into trigonal pyramidal. And the bond angles on that. So it comes from tetrahedral. So you write 109.5, but that lone pair messes with those bond angles, and you'll say it's a little less. Then the formal charge is that oxygen has 6 minus 2 electron pairs minus 3 bonds, which is +1. And then your hydrogens are 1 minus 0 minus 1, which is 0. Little note, your formal charge will add up to the charge on the molecule. I don't know if you've noticed that or not. But like notice in the case down here, he didn't have a charge. So notice all of these were all formal charge 0. Notice this didn't have a charge, and we were able to rearrange it so it adds up to the formal charge of the molecule. That's kind of a thing. So what we would do is we would say that the plus right here, it goes on the oxygen. You would still do the plus on the outside because that is the actual charge, but this formal charge adds up. We do not have any resonance because we do not have any lone pairs. Are we polar? Well, we've got a lone pair. Even though we have the same atoms on the outside, we've got a lone pair. It's going to push those atoms out of the way and in weird positions. So we are definitely polar. So if you wanted your extra credit and you watched the video, you've got your whole chart filled in. I'm going to step up here and just make sure and grab these ones also. Right here, both the molecules, both the carbon is polar, as is the oxygen. They are both polar because they have different atoms on them. The carbon has the oxygen atom on there, and the oxygen had the carbon atom. So those are both polar. And the next structure, I've got all the same atoms. So this is all the same atoms and no lone pairs. This one is not polar. And in this case, I just have 2 bonds. And so it's the same atom, 2 bonds, so this one is not polar. Resonance. None of these have a double bond that can move to other places, so none of these have resonance. And we'll just check our formal charges. We'll check the carbon. The carbon is 4 minus 4, 0 minus 4, which is 0. And the oxygen is 6 minus 4 minus 2, which is 0. And then the hydrogens, all of them will come out to be 0. Now on this guy, he has a charge, so we might expect a formal charge since it has a charge. We've got nitrogen is 5 minus 0 minus 4, which is +1. And then our hydrogens are 1 minus 0 minus 1. Which is 0. We can't do anything to fix a molecule because you can't do anything at all with hydrogens. Like you can't make double bonds, you can't move them around, they just are what they are. So this nitrogen has a positive formal charge, and notice overall the molecule has a formal charge. And then each of the oxygens are the same on here, so oxygen is equal to 6 minus 4 bonds. Minus 4 lone pairs minus 2 bonds, which is 0. So they're all good. And I want to point out something I had paused because I had glanced down at this molecule down here. You want to zoom in. Notice that this has a minus charge. Just wanted to point out that we still follow that idea of the formal charges add up to the overall charge of the molecule because I had a minus, and a plus. And notice that a minus, and plus gives us a minus. Again, minus, minus, plus, minus, minus, plus. So now you've got all your charts all figured out. Hopefully this makes more sense.